and you can state it and so on. So I can pick it up from there. Okay.
So
Yes.
like the general case is that a plus b, but the arithmetic mean is greater than or equal to the geometric mean.
Yes.
So example, a plus b by 2 is greater than or equal to root ab.
Root AB. Yeah. So this is called the geometric mean, and this is the arithmetic mean. You of course know that. And proof. Yeah. Very simple. Like, why is this true?
Yeah, so
That's probably very simple, right? So.
root a minus root
Uh-huh.
b whole squared is greater than or equal to 0 by the David inequality.
Sorry, what
No,
inequality?
root a minus root b.
Okay. Root A minus root B
Yeah, whole squared
whole squared. Yeah.
is greater than or equal to 0.
Right. And that's basically this. So yeah, that's just very good.
Yeah,
It's very trivial. Okay. What is the general version, or whatever general version that you know? General version?
like x1 plus x2 plus and so on till xn over n is greater than or equal to root n root of x1 times x2 times x3 till xn.
Right. And nth root of that. Yeah.
Yeah,
Okay. All right. Now the question is, why is this true? What explanation could you give for this? Because see, the point is not to do the proof. The point is, the reason why we will do the proof maybe is because the proof itself has a very nice technique in it. Okay. Yeah. Let's see. So why is this true for n? Because we can assume that is true for this we have proved. Yeah. Have you ever done a proof of this?
yeah.
Okay.
I think induction would be the way to go.
Okay, but how? Because as far as I know, as far as what I have done before and I've tried before, straightforward induction does not work. But still, but tell me then, how would you use? Because there's a this n is in the bottom, right? That's one of the
Yeah.
problems. Yeah.
So like we can do induction on n.
Uh huh. Induction on n. Okay, let's see. So you would.
Like the proof I've learned is that we can like do an induction on n and then we can prove that n is we can take the base case as 1 and then we can prove that n equals to 2 is true, n equals to 4 is true, n
Okay.
equals to 8 is true, and like all the powers of 2.
Oh, okay, okay. So that's a different type of induction, yeah. So for all
Yeah,
powers of two, it's okay. So I'll take that because that I think it's quite comfortable for that. Okay, all powers of two done. Okay,
yeah.
then what? Then what?
Then with n we can prove that n minus 1 is true.
Uh-huh. Okay, okay. So yeah, so this you see the general trend. Okay, whenever you have a statement which you can prove for infinitely many things, okay, it just doesn't have to be this particular sequence. If you can prove for infinitely many things, then this is something what you do, right? You assume for n
Yeah,
and prove for n minus 1. Okay, so then I will just edit this statement and I'll ask you to fill the details of that, because that's the interesting part. Assume this and prove for n minus 1. So basically just change the variable names and take n minus 1. Let's see. Because here is the art of substitutions and so on that you'll have to use the manipulations to actually do this.
yeah,
Okay. So of course we are assuming this for particular n, right? Particular. Otherwise, don't put n equal to n minus 1 there. Particular n. Yes. And then we'll be done for all numbers.
yeah.
That's okay. So then what are the details of this? So you have to go from the first one to the second one. So you have to write a mean of n minus 1 numbers as a mean of n numbers. That's a trick. You have to do some trick
Yeah.
for that. Okay. So what do you think we can do? Certainly we have to choose some values of xi in a smart way, right? So that it actually turns out to be n minus 1 values in the end, right?
Yeah.
So yeah, so I'll just take one step forward. So if so what I'll usually say is that don't try to disturb too many things here, right? So we will keep the n minus 1 stuff maybe like this or what? Okay, never mind. I'll think this is where there's a lot of flexibility, so I'll let you say it first.
Yeah.
Yeah. But I can write a general version still. Write this as a mean of n minus 1 things. This is where you have to put the art of inequality. N minus 1 things. It doesn't have to be these specifically, otherwise it will be very hard. Maybe, yeah, but just try to write it as mean of n minus 1 things. Actually, this is a very general technique that we learn here that later on you can apply in something called convex functions. That's Jensen's inequality comes from there, which is a
Yeah.
generalization of this. So how do you do that? So I will choose a specific value for x. Yeah, please say. Yeah.
We can take like an equal to the average of.
Sorry, I can't hear you. Something is with the volume. It has changed. The voice has changed.
Yeah. So
Hello.
like,
Hmm.
hello.
Yeah.
So I was thinking that we can like take an as just the term itself, like a1 to an minus 1 by n minus
Oh, no, no. I'm losing your voice, and there is some feedback. There is some. I don't know. Some feedback coming. I don't know what that exactly is. Um,
1.
Maybe just adjust the. I think just turn the jack or something like that.
Yeah,
Just see it. Yes.
this better.
Try saying a bit more.
Yeah, is this better?
Yeah, now it's perfect. Yes, go on.
Yeah, so I was saying that maybe we can let an equal to the average of a1 to an minus 1.
Okay, an or xn or an. Yeah, okay. An, the average of an to n minus 1. Okay, so that's n. Makes sense. Yes.
And then we can just use the first statement. So
Mm-hmm.
like a1 plus a2 plus and so on.
Right. Yeah. So I think, yeah, this will work out. Yeah, you're right. This will work out. So I'm not going in the details. Okay. This will work out,
Yeah.
right? Because as you can, yeah, you only said me, so it's, you know, that it will become n and this
Yeah.
n will cancel and so on. Very good. Then you know this. Yeah, very nice. Very cool. Yeah.
Yeah.
So now I would just still want to see this in a more general way, because as you probably have heard, there's a generalization of this, which is more important in problems sometimes. But still, first of all, I would just like to talk about this log function, not talk about it, just the graph of it. Okay. So we all know that the log function is an increasing function. That's number one,
Yeah.
right? And number two is that it is, if I just say this statement, decreasingly increasing, can you unpack this?
Yeah.
Mhm.
Like as it's increasing, it slowly stops increasing less and lesser.
It doesn't, yeah, it doesn't stop, but its acceleration is negative, right? It
Yeah.
something like that. So you meant that only, yeah. So this something like this. Okay, now you see with these kind of functions something very specific happens. So let's just take for two. Okay, maybe I'll just exaggerate the thing, okay, so that I can explain better. Now if you take, let's say three, let's take 2 points for the time being. Okay, let's take 2 points. Now if you evaluate these two functional values, so I'm not going to do Jensen's inequality, I'll just connect this with AMGM and leave it. Okay, so let's say there are two values. So there is f of x1, this is one height, and there is f of x2. Now if you decide to take the average of these two heights, okay, average, so that height would somewhere be along this line, right? And if you decide to take the coordinate as at x1 plus x2 by 2, then it would not be on the curve, right? It would be below the curve, isn't it? So this is where the average height would be. Okay, so just saying this is f of x1 comma f of x1, x2. If it's too easy, then I'll not say the details. Otherwise, I'll just say okay. So this, and this is where this height f of x1 plus all that is. So this is p. Okay, this is our p. Okay. Now the second thing is that if you instead first add the values, meaning that you evaluate the function at the average, okay, then the value would be a little higher, isn't it? So I'm just writing the height. Okay, so probably there's no need to keep this here. Just showing you a more continuous version of this AMGM. Okay, and so something like this. Okay, this is higher, right? So for any function, like any function which decreasingly increases, better studied when you study derivatives and such in terms of slopes, because that really captures the point. You can say that the average of the heights is less than the height at the average. Okay, maybe less than equal to. Is that okay? Yeah. Now the second thing is that I